Hello, my name is Luke, and welcome to this PyTorch tutorial series. In this video, we're going to look at how we can combine the attention mechanism to an LSTM in order to improve its performance. If you're new to this channel, all my code that you see here is available for free in my GitHub repo, link in the description. And as I said, this is part of my PyTorch tutorial series, and you can look through the playlist here. In that previous video, we looked at the attention mechanism by itself, what it is, how it works, what it can be used for, but we didn't really give an explicit application for how we would implement this to sort of improve some neural network type. And in this video, we're going to see how we can use it to improve our LSTMs. So if you're new, remember to subscribe to stay tuned for future videos. If you're not familiar with LSTMs and attention, go back and have a look at those previous videos. So we hinted on in those LSTM videos how there may be an issue with the fact that we're trying to encode the whole sequence and fit it into a fixed sized buffer. That memory, in my diagram here, that memory and hidden state cells that we're trying to pass in terms of our long and short term memory to itself in order to encode an entire sequence. We have this fixed size buffer that kind of limits the amount of information we can fit into it, but also LSTMs and similar recurrent network types have the ability to add and both forget or remove information from that buffer, which potentially gives rise to situations where our network has decided not to add a certain piece of information or has decided to remove a certain piece of information from that buffer in the sequence. And then, if it hasn't been added or it's been removed, there's no way to go back and then decide, oh, I actually needed that piece of information, and go back and retroactively add that to the sequence. There are sort of bidirectional networks that try to do that, but with vanilla LSTMs, there's no real way. With attention, on the other hand, what we can do is, as well as passing that output for our LSTM to sort of our classification head, if we're doing text classification or next token prediction, we can pass that into a buffer, or basically store that output for every time step and use that as the keys and values for our attention mechanism. So you can see in this diagram I've created here, we're storing each of the outputs from the LSTM at each time step. And what we're doing is we're allowing the LSTM at our current time step to produce a query and then query all of the values using our key value pairs, query the outputs of all the previous time steps from our LSTM. What that allows us to do is select any piece of information from any output at any point in time in our sequence without having to worry about whether or not that information is contained in that hidden or memory cell buffer. So at our current time step, we can decide, we have full access to all of the tokens or all of the outputs from all of the LSTMs. So we don't have to, again, decide early on whether or not a piece of information is useful or not. We can, at our current time step, look back at all of the outputs and say what is going to be useful, what is going to be not useful right now. So I haven't drawn the attention mechanism on here. Again, we talked about that in the previous video, but we're going to store the outputs from our LSTM at each time step in our buffer, and then we're going to use the PyTorch's multi-headed attention that we saw again in the previous video. And that, if you remember, we have a linear layer that's going to project the key and values to a key value vectors. So we're going to use the same outputs for our LSTMs as the key and value inputs, but then we have another layer that will project to the actual key value vectors. But again, only the current time step is going to produce a query to query all of the previous time steps. So the task here, we're doing text generation. This is the same task that we looked at in the text generation with LSTMs videos. And so I'm going to skip most of that. If you want to go back and understand the code there, I recommend going back to this video. The tokenization and vocab training, vocab creation is the same as that. We're using the sentence piece tokenizer, and we're also using that AG News dataset from there. I'm going to skip over most of that. I think the only difference here is that I'm also just doing a little bit more filtering. I realized that in the dataset we had these hashtag 39, 38, 36s. I wasn't too sure what they were at the time, but I realized that they're actually ASCII codes for symbols that for some reason, when they did the original scraping of the dataset, weren't passed correctly. So I'm just replacing them with the true symbols, because we ended up getting a lot of hashtag 39s in our generated outputs, which is a bit annoying. So I've just done that when I filtered the data set for our tokenization model, and also for our actual data set, I'm doing the filtering there on the pandas data set as well. So that's all I've done. Again, just uncomment this if you want to train the sentence piece tokenizer, and then that's all the same as well. This is all pretty much the same. We can skip right down to our actual model architecture, which again is very similar to what we had before in the LSTM text generation. But now you can see we've got this multi-headed attention block here. Again, we covered that in the previous attention video. So we can have a look at our forward pass and see what we've changed now. You can see as an input, we're also taking this hidden sequence. And so this is just a list of the outputs of the LSTM at all of the previous time steps. So you can see here, we have our index of our token, we get our embeddings, and that goes into our LSTM, as well as that hidden in-memory buffer. And we get the output and the next hidden in-memory buffers there. And you can see we are logging the output of the LSTM at the current time step to that list, to that buffer. And then we're going to pass that as an output for the next time step as well. So in our actual training loop, we're going to manually loop through the sequence for our LSTM as we did really early on. So because we need to take the output and then put it into our attention module to query the next step, we're going to do it manually, one step at a time. There is a way to pass it the entire sequence like we do with the LSTM normally with causal masking and stuff for our attention. But we're not going to cover that in this video. We'll cover that in a later video. But if you are interested, you can have a look at causal masking for attention. But in any case, what we're doing here is we're just going to concatenate that sequence into a single tensor. We're going to concatenate it on the dimension, or the second dimension, so dimension index 1. So we'll have batch size by length of sequence by size of that vector, which is going to be 256, as you can see here. So this hidden cat, that is this buffer of vectors, the output of every LSTM at each time step. So that's what that is. And as I said, that is going to go into our attention block as the key and value. And again, PyTorch's multi-headed attention block has another linear layer that is then going to project this key and value that we've given it to the actual key and value vectors that then go on to do the attention in the attention mechanism. The query, again, is just the output at the current time step, putting that in as the query. So we'll have one query per head. You can see here that I've got 8 heads, but don't worry about that at the moment. We've got one query, and then each of these is going to be the length of however many steps there has been so far in our sequence. Again, with one query, we're going to get one output. And again, we have our attention outputs, and then we also have the attention mask or the attention map outputs as well, but which we don't really need. But this is just the output of our attention block. So again, we're going to query all the previous time steps. We're going to multiply it by our query by our keys, take the softmax, multiply that by our values, take the sum of that over our queries, over our keys, and then we're going to get a single vector output. And what we also are going to do is something that's typical with attention is we're going to treat it as a residual step. So we're going to have output from our attention, and we're going to basically add that output or the input to the attention block, the output of the LSTM on, and so it's going to be a residual skip. So we're going to have this residual skip over attention. Attention does take a little while to train. It is a bit slow to train, and so we want to make sure at the start of training there is some way at least for our model to actually learn, and then slowly it'll learn to properly do the querying of previous time steps. But first we want to actually make sure there's some information in the output. So doing this residuals connection allows for that. It also allows for gradients to skip over the attention block. We have a softmax in there, and it is a bit of a complicated mechanism, so it can mess around our gradients a little bit. So having that skip connection there also helps. In any case, we take the output of that, pass it into our final little MLP here, which will then do the prediction of the next state token. So hopefully that makes sense. We got our output here. We have the current list or buffer of the outputs, as well as the hidden and memory cell buffer. Everything else here is pretty much the same. We have a few extra parameters. Now I think we have the same number of parameters here, all the same. And our training loop is a little bit different. Like I said, we're manually looping over our sequence. rather than passing the whole sequence and letting PyTorch's backend do the looping through the sequence, which is a lot faster. But again, because we're trying to log the outputs and pass it and do the querying with the attention, it's just simpler to do it this way. But like I said, there is a way we can do it with causal masking, but don't worry about that for now. All right, so we have our hidden and memory buffers for our LSTM. We're also initializing the hidden sequence list, and we go into our loop, and we're going to take the current token, the current time step for the input, and the output token is basically going to be the next token in the sequence, where I've already randomly shifted them up here. So the current token in my sequence, and then the next token in the sequence is going to be my target. So input token is my input, hidden sequence is the current list, and then a hidden in memory buffer. We get our prediction as well for the current time step, which is what we're using to, we're going to train that to predict the next state token. Again, we have our new hidden sequence, which we're going to pass back in, and in our memory block, we're always just adding on current output. The very first time step, that list is going to be empty, but we're adding on the output at the first time step first before we do the attention. So for that very first time step, it's just going to be able to query itself, right? So that's why we're adding the current time step to the buffer to create the keys and values as well, so that it can at least query itself, which is probably not that useful at the first time step, but that's fine. Later on, that buffer will fill up with all the previous outputs. Okay, so then we add in the loss to a loss logger, and then we just divide it. So we take the average loss over the sequence, and then we do our training step there. So I've already trained this model for quite a while. This is probably several hours of training. Again, you can see the loss is quite noisy because, again, we're not looking to accurately predict exactly what the next token is going to be. We're looking to learn the distribution over tokens. So to see how we can generate text now with this attention mechanism, let's have a look at some examples here. So we'll have our input prompt from our article. Let's find a good one. So the same as before in our LSTM text generation, we have our article that we're trying to predict the next token on, and we have that title separated by a colon, and then the contents of the article, and we're going to feed the title as the initial sequence and get our model to continue on that text generation. And because we've put the colon there, we're prompting our model to now produce the contents of the article. So let's have a look. So here's our prompt. So Yahoo launching music downloading service this year, and here's the original content, right? And here's the tokens that we've got. And we have that colon as the last token in our sequence, which is hopefully going to prompt our model, if it's learnt correctly, to now produce the contents of the article. So how this is going to work is similar to before with our LSTMs. We have to initialize our hidden in memory buffer. We don't need to actually do this. The LSTM block will initialize to zeros if we don't pass anything in, but we're going to do it manually here. And we also need to initialize that list of the outputs of our LSTM. And we're going to just manually pass in the tokens in our input sequence here, one at a time in this initial loop. And again, it's going to fill up the list from our hidden states, and also going to pass the memory and the hidden state buffer for our LSTM. So once we've done that, we can now start to predict the next token in the sequence. We're just taking the output of the current step and then sampling from our distribution, again, discounting by the temperature to get a next token in our sequence. And then we're putting that next token into our LSTM again, and going back and over and over again and generating our tokens iteratively. So put that into our LSTM again, and sampling and putting it back in over and over and over again to generate a whole sequence. And we're going to stop after 100 iterations, or we're going to break early if our model produces that end of sentence token. If it's learnt correctly, produce that end of sentence token, and we'll stop early. You can see we've done 38 time steps, and we've obviously reached the end of sentence token, and we can have a look at what it has generated. So here's our initial title prompt, and this is what we've generated. So Internet's online music service is to launch a new website for music downloads, including the company's new service and the Internet's latest version of its online music store. So there we go. It's produced a pretty coherent sentence. It's kept the theme of music downloading, hopefully that attention mechanism, because even at the very end of our sequence here, it's able to look at the entire sequence and can see that in the initial prompt, we talk about music, we're talking about music multiple times, and we're talking about music downloading service or music online music store. So hopefully that attention has allowed for a better, more cohesive sentence that it's produced, and it's kept on theme for longer as well. So one thing we didn't look at before, we did look at the probabilities of the output distribution, but one thing I thought might be interesting is to actually have a look. Let's generate another sentence, and we're going to stop early, so we'll stop before we reach the end of sentence token. Internet's online music player is to be the. So here we're looking at the distribution over the tokens for the last token that was produced, so the. So you can see we've got a number of tokens here, and I've got the temperature pretty low, 0.3, so it's quite low. So you can see it's a pretty flat distribution with a few spikes there. So let's have a look at the top 10 spikes. You can see the wasn't actually that high in this sequence, so able to be able was actually the highest one in that sequence. Let's have a look at another one. So here is in talks. So talks was actually the highest probability, as you can see here, and we did sample that one. So even if it has quite a low probability, there is a chance that we can still sample it. So new video was a very high probability in this distribution. That was the highest one, so we sampled in a new video. So you can see how, if it wasn't apparent already, we build up this sentence by sampling from this distribution. As I said before, we're not looking to exactly predict what the next token in the sequence is going to be. We're looking to produce this distribution. So unlike classification, if we were doing like a sentence classification or even image classification, we'd hope to be very confident. For one of the classes, we're actually looking to produce this distribution and being able to sample from that iteratively to generate our whole sentence there. So here's all the potential next tokens we had. So in a new service, in a new music, in a new version, in a new game, in a new online, in a new internet, etc., etc. And of course, what sentence or what token we sample in this time step will then drive the distribution of tokens in the next time step. And so we're sort of randomly steering what this actual sentence ends up being about. Again, the attention mechanism allows us to attend to all the previous tokens and really stay on track when we're generating and not forget what the actual earlier time steps we're talking about. Okay, so that's all I really wanted to cover in detail in this video. But looking at what we're doing here and incorporating the attention mechanism, you may start to be thinking, okay, well, if I have this attention mechanism and I can query all the previous time steps, then really what is the point of the LSTM? Or is there some way we can actually just remove the LSTM altogether and just use attention? Could it be that attention is all you need when creating a iterative or a sequential model? And we'll see that in a future video, how we can potentially remove our LSTM, remove any recurrent part, and see how we can construct our network to purely just use attention and the benefits that might bring. In any case, that's all for this video. Subscribe if you haven't to stay tuned for the future videos, and I'll see you in the next one.